Welcome to the 9th installment of the probability section of the ProbStats course. Today we're going to talk about expected value and variance. And so expected value is the average outcome of a probability experiment, and the square root of the variance is the standard deviation. So now we're talking about means and standard deviations, and this is going to help us tie in to connect to statistics. This is how it works. So let's start with an example of a probability density function. This is really simple, just to illustrate the calculation. So here's our tabular form of our probability density function. And so we have this spinner and we get these outcomes. We've labeled these areas with different values. So the outcomes are the values x, this set x, the little x can take on the values 1, 2, or 3, and they have associated probabilities. So this tabular form is perfectly fine for a PDF. And here are the formulas. So the expected value is just going to be the sum of products. So products of what? Well, I'm going to take each outcome, and they have to be numeric, each numeric outcome times its probability. So, and then I sum them all up. Now, I didn't do I equals 1 to n because this isn't necessarily finite. It's discrete. But for example, with a geometric PDF, I would have infinitely many. I would have an infinite sum. It would converge, but I'd have an infinite sum. So I'm just using I as my indexing variable here to indicate that we're going to sum over every possible outcome in the probability space. All right, and we're going to call this value mu sub x. Mu sub x, mu standing for the mean of the probability experiment. And the variance and standard deviation, the variance is calculated on the way to the standard deviation. The variance is a similar calculation. You do the expected value of x squared, which means I just square the outcomes and do the same formula as expected value, times the expected value of x squared. Well, that's the mean that we calculated before. So we already have this value from before. We're just going to square it. So this is the main calculation that we do for variance. And then the standard deviation is the square root of the variance, or the standard deviation squared is the variance. Why do we prefer the standard deviation to the variance? Well, look at this. This is squared outcomes. So let's say the outcomes were in dollars. This is dollars squared. And then the average, if all my outcomes were dollars, the average was dollars, but then I square it. So this is dollars squared. So the units of the variance are actually the square of the units of my outcome. But when I take this square root, the standard deviation will have the same units as my original outcomes. So generally speaking, the standard deviation makes a little more sense, but variance is a nice descriptive word. It's measuring how far apart the outcomes are, how widely scattered they vary. So let's jump back to our example and make sure, and just show these quick calculations for the mean and for the expected value, variance, and standard deviation. I copied the t-chart over here so we can see what we're doing when we're calculating the expected value. Right, I'm writing the expected value of capital X is equal to, I take the first outcome times its probability. So I'm going to have 1 times 1/6 plus 2 times 1/2 plus 3 times 1/3. And this isn't that hard a calculation. I have 1/6 plus 1 plus 1, which equals 2 1/6. Okay, so that is our mu. That is the mean or average. On average, we would expect the value of this spin to be 2 1/6. Okay, So now we need to calculate the variance. To calculate the variance, we are going to do the exact same calculation as we did right here, except we're going to be squaring all of these values. So let me show you that. Expected value of x squared is going to be 1 squared times 1/6 plus 2 squared. So I'm just squaring all the outcomes. 2 squared times 1/2 plus 3 squared times 1/3. All right, so 1/6. Now I have 4 halves, which is 2, and now I have 9/3, which is 3. So the expected value of x squared is 5 1/6. Okay, so my variance is equal to the expected value of x squared minus mu of x squared, which is going to be 5 1/6 minus 2 1/6 squared. Oops. Squared. Which is going to be equal to 17 over 36. Okay, so now the final thing is we want to take the square root. So the standard deviation, the sigma sub x, which is the standard deviation, is going to be the square root of the variance. So that's going to be equal to the square root of 17/36, which is going to be equal to approximately 0.687184. Okay, so that's what we mean when we say let's calculate the mean and the standard deviation. Right, so the average is 2 1/6, and the standard deviation is about 2/3, right? That decimal was 0.687, so about 2/3 is the standard deviation. So let's just jump back up here, right? So all we're doing is we're multiplying these products together, right? It's just each outcome times its associated probability, add them all up. Then the next step in the calculation for the variance, we do the same thing, but we do it with the outcome squared times its probability, associated probability, and then sum them all up. Then I subtract, to get the variance, I take the expected value of x squared and subtract the expected value, and then I can take the square root. So those are the steps. Now this example is also in the course notes for this section, and I don't often do that. I try to keep the examples in my videos different than my examples in the course notes. That way you have double the number of examples, you see more situations. But here I'm going to do this because I'm going to show you how the graphing calculator can help us. So let me go back to this example and let me show you what the graphing calculator, what we're going to use it to do. So if we just have a table of probabilities, it's T-chart with PDF in T-chart form. What we can do is we can go to our stat list editor and we can clear out some lists. I'll just get rid of these. Probably should have done this, paused the recording and done this, but to clear out a list, you go up until the list name is backlit, you hit clear and then enter. That's what I was doing. Okay, so now what I would like to do is I would like to put I'm just going to copy this T-chart into my calculator. So I'm going to have 1, 2, and 3 in my first list. Then I'm going to arrow over to my second list, and I'm going to put in the 1 divided by 6 and 1 divided by 2 and 1 divided by 3. So notice it converts to decimal form. So this is a cool thing that our calculator will do, and it's actually using the ability of our calculator to interpret frequency tables and to calculate the mean and the standard deviation to calculate the descriptive statistics for a frequency table rather than just a data set. But it turns out to do exactly the calculations we need. So let me show you how that works. I'm going to go to my stat button, calculate menu, and I'm going to do 1 var stats, not 2 var stats, 1 var stats. And when I do that, it pauses here, so I have time to type in second L1, comma, second L2. So I'm saying, hey, I'm giving the outcomes in L1 and the probabilities in L2. Why don't you multiply them together and then give me the mean and the standard deviation, as if it were a frequency table. And notice that we have exactly the values that we calculated before. It gives me 2 1/6 for x bar is its mean. So we wrote mu sub x, but x bar in statistics is what we use for the mean. Notice that the sum of x, that's the expected value of x. Expected value of x is the second line. The expected value of x squared is that 5 1/6 that's right here. So then when it does the 5 1/6 minus the mean squared and takes the square root, it gives me the standard deviation. It does not give me the variance, and that's fine. It gives me the standard deviation and gives me check steps along the way to make sure that I can see that. Now, on a test, are you allowed to omit the work? No. But you're certainly allowed to use the graphing calculator to check your work. And again, it provides these check steps along the way, so you can at least make sure you're not going awry when you do the work on a test. So let's jump down to example 2. And this is a poker hand. And we've done this example before, so I just wrote down the probability density function. So we're choosing hearts to go into our hand. So 13 choose x, so whatever number. Like if x is 2, we do 13 choose 2 because we have 13 hearts. So from that part of the partition, right, from that subset in the partition, we're going to grab x cards. Then from the other 3 suits, right, from the other side of the partition, those 39 cards, we're going to choose the rest of the 5 cards to go into our hand. So again, if it's 2 cards that we've already chosen that are hearts, then we're going to choose 3 non-hearts to go in. Okay, so let's write down this expected value. And so our expected value is going to be, it's going to start with a 0, right? The probability that there are no hearts in our hands. And by the way, it doesn't really matter what this term is because I'm multiplying by a 0. So I'm just going to leave it for a second. And you'll see the pattern with the 1. So what do I do? 1, well, the probability of getting 1 heart is 13 choose 1 times 39 choose 4 over 52 choose 5 plus, and then I have a 2 times 13 choose 2 times 39 choose 3 over 52 choose 5. And I hope you can see how this is going. So I'm going to have plus 3 times 13 choose 3 times 39 choose 2, 39 choose 2 over this same denominator. Let me slide this up. Let me try sliding this up. 52 choose 5. And then 4. So we have 13 choose 4 times 39 choose 1 over 52 choose 5. And finally we have 5 times, and this is 13 choose 5 over 52 choose 5. Okay. And then what would we do to calculate the expected value of x squared? So just watch here, because I'm going to switch colors and just show you. If I want to calculate expected value of x squared, right, then I just square everything. Squared, squared. So 1 squared is still 1, but 2 squared is 4, 3 squared is 9, 4 squared is 16, and 5 squared is 25. So just the green shows the calculation for the expected value of x squared, and the green plus the red, the green shows the expected value of x calculation. The green plus red shows the calculation for the expected value of x squared. But what I'm going to show you is how to do this in the graphing calculator to help us. You can actually evaluate these on the graphing calculator. It's not that difficult, it's just a little bit tedious. But let me scroll down here so we can see this probability density function. And let's pull our graphing calculator in here. So this is what's explained a little bit in the notes, but it's so much better to see here. This is why I chose to do this example. We're going to do this stat editor list example, but it turns out that there's a spreadsheet-like functionality that we're going to be able to take advantage of. So I'm going to clear out these lists, and I'm going to show you these calculations performed by the graphing calculator. So first I need the 0, 1, 2, 3, and 4, and 5, right? Those are my outcomes. Those are all possible outcomes there in L1. And now L2, I'd like to write a formula. I basically am going to be writing this formula right here. So how my graphing calculator does that is when I notice this. So look at this input line. Look at the input line right here. As I, my apologies. Wait, I need this and this. So look at this input line as I arrow up. As I arrow up, it changes to L2 equals. So there it is, arrow down. This just says I can put an entry in, and it'll be this single cell right here. But when I arrow up, it says, hey, I can write a formula for the entire list too. And I'll be able to use these hotkeys down here, right? This L1 hotkey, I'll be able to use it as a variable in this formula that I'm going to write. So here's how it's going to work. I'm going to type 13, choose X, right? Well, I'll go math, probability, right? Option 3. So 13, choose X, but X, what I want it to do is I just want it to jump over here, and for this value, I want it to use the value just to its left. So I'm going to go second L1, right? So 13, choose whatever is sitting next to me in L1. And what I want to do is multiply that times 32, math, probability, NCR. So 39, choose, and so let me put in parentheses. Now I want to do 5 minus whatever is sitting next to me in L1. Okay, and now I want the division of, and then I want 52, choose 5. So math, probability, option 3, 52, choose 5. And there we go. So now we have the associated probabilities. Now we've actually created the T-chart version of the PDF in our graphing calculator. Now I'm going to do a couple of things. Eventually I'm going to calculate the mean and the standard deviation this way. But first I'm going to quit out of there. And what I want to do is I want to add up all of the values in L2. Why? Well, those are my probabilities, and if I've done the formula correctly, they should add up to 1. Happily, they do. Okay, so that's nice. And then now I can do the same thing as I did before: stat, calculate, 1-bar stats, and put in the two. You put in the outcomes, comma, the probabilities, and then it does this calculation. And notice that. Right, so we know that the expected value is 1.25, and we know that the expected value of x squared is 2.426, and that the standard deviation is 0.929. And you'll see these calculations worked out in the course notes as well. So again, just wanted to show you this with the graphing calculator, so you'd be able to see that. So I'll apologize in advance for the morbid example, but this is what actuaries do. They help insurance companies price insurance policies. And of course, insurance is an investment that we don't want to pay off. Dave Ramsey is a great financial advisor, and he makes the point that we want insurance investments to be bad investments. We buy what we need and we hope we never need it. Buy what we should have and hope we never need it. So, but this is a great time to talk about actuarial sciences, because this is the perfect first course for somebody interested in taking the actuarial exam 1. So let's see if we can figure this out. So we have this insurance company, and they're going to sell a 20-year term life policy, which means for a term of 20 years, you get the benefit if you pass away. Okay, so the actuaries figure this out. They go through tables and they figure out what the probability of someone dying before the end of the term of the life insurance is. And in this case, 50-year-olds have a 97% chance of living the next 20 years. So only 3% of them are going to pass away. And so the question is, what should the total price of the insurance policy be if the company needs to earn $500 per policy they write? So there needs to be enough of the total price to pay for the times that they have to pay out the $250,000, but they also need to earn $500. Okay, so the T-chart that we have has two probabilities. It has the 97% chance and the 3% chance. Okay, and when the 3% chance well, let's do it this way. All right, so we have X and P of X. Okay, so let's look at this as the total price. I'm going to put T in as the total price. So 97% of the time, the customers pay the total price T. They pay it over 20 years, as you saw, but we're just going to assume that they pay one lump sum at the beginning to make the calculations easier. But they pay whatever the total price of the policy is, and then they're covered for 20 years. And 97% of the time, that works out for everybody. The insurance company makes money, and there's no funeral. Now, 3% of the time, it's unfortunate, but this is why we have the insurance, so the family can be taken care of. And what happens, this is from the insurance company perspective. So for them, it's a $250,000 loss. Right? They have to pay that out. That's a debit that they have to pay. But since we decided that they pay the total price of the insurance policy at the beginning, they do get that premium. Okay, so we have the premium 97% of the time they just get the premiums, and then 3% of the time they get the premiums, but then they also have to pay out the benefit. So the question is, we want to set T, right? And not just T, but we want to add $500 to T once we get it. That was what the question asked for. Well, let's calculate this expected value. And so I have 0.97 T plus the minus 250,000 plus T times 0.03. So notice that I just end up with T minus 250,000. Right, so the 1T is coming from the 0.97T plus the 0.03T. Then I have the minus 250,000. Times 0.03. which is $7,500. Okay. So what does the insurance company want to do? Well, the insurance company will want to set T equal to $7,500 so that the expected value of these policies that they write comes out even, right? That they're taking in enough money to be able to pay the benefit when they need to. The question though said that we wanted to add $500 to that because that's going to be their profit. So they're going to set the price of this policy at $8,000. So that's the kind of problem solving that might be expected in an expected value computation when you're given some sort of situation or scenario where you set up the expected value with a variable in it, and like this one was t, and solve for t. But that's expected value and variance, or mean and standard deviation, and that will provide a good tie-in for starting statistics.